Hello, welcome back. So today we are talking about, we're starting our unit on light. So this is Light Matters 6A. So I'm going to start with doing the quick review up at the top of the page. Use the word bank there. Pause the video, fill it in as best you can, and then come back to get it checked. Welcome back. Here we go. All right, sound travels in compression waves, also called longitudinal waves. And if you put compression here and longitudinal here, that is fine. Light travels in transverse waves. The parts of a transverse wave are crest and trough. Amplitude is the maximum distance that a particle moves away from rest, and frequency tells us how often the wave occurs, how many times the wave passes. All right, pause it if you need to, but I'm clearing and moving on. All right, so we know that light travels in transverse waves, which means that the energy travels at right angles to the direction of travel. Now, what does that mean? We've talked already that if sound traveled like this, it wouldn't make it to your ears when you're in the room with me. It would get lost. Sound doesn't have a whole lot of energy, so it's got to travel in a compression wave, so it has any chance at all at getting to you. And we know sound doesn't have a lot of energy because when we are outside and we're trying to holler at somebody, the wind can just carry our voice right on away. So we know that sound it doesn't have the same amount of energy as light. Sound also moves at a slow enough speed that we've broken the sound barrier. We are nowhere near traveling at the speed of light. So what does that mean, traveling at right angles? Well, if I'm a sound wave, I can come straight at you in these bursts of compressions and rarefactions. But if I'm a light wave, if I come straight at you, I'm going to burn your face. I'm going to blind you and I'm going to burn your skin. So what light does is, yeah, I'm coming at you, but I'm going to go this way, and then I'm going to go this way, and then I'm going to go this way. And I'm getting to you. I'm just got to go back and forth in my method to get to you. Okay? So that happens in switchbacks. So these are all examples of switchbacks, switchback trails, switchback roads. This one is from the Grand Canyon. That's a donkey trail in the Grand Canyon. Can you imagine that? Woo! But yeah, this is where we want to get, and this is where we are. We can't go straight up. We can't go straight down. Too much energy. What would happen if you tried to go straight up or straight down a really steep thing? Right. If you go straight down, you're going to end up with a poof, right? Or if you try to go up, it's just so much energy. You just can't. So what we do instead is go back and forth and back and forth and back and forth. And by doing that, by switching back, you end up being able to get to the top of the hill without expending as much energy or hurting yourself. This one here is one of my favorites. That's a road. Like that's an actual road. That's an ATV trail in Utah, but that's a road in China that cars actually drive on. There are some crazy roads out there in this world that are not maintained by VDOT, and these people manage to make it every day. So here's basically what ends up happening on a switchback. So you end up making these big loops as you drive to get up or down the mountain. So that's what a transverse wave does. Like a switchback. Now, light waves are not mechanical waves. And what that means is that they do not require a medium to travel. And why is this important? Think about that for a second. Why is it that we think it's really awesome that light can travel without a medium? Exactly, because sunlight reaches Earth through the vacuum of space. If light did not travel through a vacuum, if light required a medium, we wouldn't be here. Because there's nothing out there in between us and the sun. So the fact that those light waves can get to us and keep us warm, grow our food, get the water cycle and the wind cycle going, very important to us. All right, there are three things that can happen when light hits an object. It can be absorbed, it can be reflected, or it can be transmitted. So what happens to light? Art. Absorbed, reflected, transmitted. Art is what happens to light. Most objects are opaque. And opacity just means that light doesn't go through them. So the light is either absorbed or it's reflected. So, for example, the tables in the classroom, or, well, since you can see it, this mouse is black. And it appears black because most of the light that hits it is absorbed and very little is reflected. This appears white because most of the light that hits it is reflected and very little is absorbed. This appears green because it reflects the wavelengths of light that appear green to us and absorbs all of the other wavelengths of light. Sometimes objects can let light through. So translucent objects allow some light through, but it's going to be scattered. So smoke, so dirty air, smog, fog, frosted plastic, frosted glass, sunglasses, stained glass, colored glass, and colored plastic. All of those things are translucent. They let light through, but you wouldn't want to read through them. So, like, for example, here's a frosted plastic jug. Light does go through it. Like, we can see light through it, but you wouldn't want to read through it. It's not clear. Transparent is when the light goes through completely. So clear objects, clean air. Like right now, there is a medium between me and the camera, but we can see each other because it's clear. It's air. It's clean air. Clean water, clean, clear glass, clean, clear plastic. All of those things would be transparent. But both things are considered to transmit light. All right, pause it if you need to, but I'm going to clear and scroll up. All right, so our examples here are define and give examples. An opaque object absorbs or reflects. And I want you to think of something that's opaque. Good job. So a tree, a table, a book. Now, humans technically are opaque. We stand in the sun, there's a shadow. But if you put a really powerful flashlight under a human hand, right, we kind of become translucent. So it's debatable. So translucent means that it transmits partially. So it lets some of the light through. So that's going to be smoke, fog, frosted glass, frosted plastic, stained glass, colored plastic. And then transparent, it transmits fully. So clean air, clear glass, clean water, clear plastic would all be transparent. All right, again, pause it if you need to, but I'm moving on. All right, so reflection is what we're saying happens to some of those light rays. So what is reflection? Reflection means bounce. So reflection means that the light rays bounce off the object. And there are two types of reflection. Now, if I ask you to think of reflection, you think of a mirror, exactly. So the reason why a mirror, and think about it, a mirror reflects all of the light that hits it. It absorbs none. It is opaque, and it reflects all of the light that hits it. So there are two types of reflection. So I've told you that light is hitting, for example, this shirt, and it is being reflected off of it, but you can't see yourself. Can you imagine if like all of the things in the room were reflective surfaces? Like how crazy would that be? Woo, it'd be really weird, hard to focus. So when it happens that we can see ourselves, like in a mirror or in a piece of shiny metal or the side of a car or in the refrigerator or in a glass window, that is called a regular reflection. And that happens because, now I know that's not completely flat, so just forgive me, but that happens because it's this flat, even, smooth surface. And so when the light rays come in, they're all coming in at the same angle, And when they hit and reflect, they go back out at the same exact angle that they hit. And the lines are all still nice and even and parallel. That means you can see yourself. But what about the things that you can't see yourself in? So I was talking about my shirt. So look at your shirt. Look really closely at it. So to look at it, to feel it, it appears flat and smooth. But when you really look closely, what do you see? Right, it's all woven from the material. So it's not really flat. So that means when the light rays hit it, they get scattered all around. Let's see what that looks like. So again, oh, my little picture thing's in the way. I can move it though, can I? Yes, I can. All right, so, except it's dark. Oh, it went away entirely. Oh no, well, y'all don't need to see me. All right, so we've got our diffuse line, and it's bumpy, and it's irregular. And it shows the weave of the fabric. And again, the light rays are coming in at the same angle they came in before. Light rays don't hit an object differently because the object isn't flat, but it does reflect differently because the object isn't flat. So this one's going to go straight up that way, and that one's going to go off that direction, and that one's going to go this way, and this one's going to go off that direction. And in that way, we don't have that regular, even, smooth surface, so you can't see yourself in it. It's a diffuse reflection. It has been diffused instead of being regular. And we already said that a mirror is the thing that we most associate with reflection. All right, I'm going to see if I can get the camera back. I managed to get it back. Okay, so moving on. When you were in third grade, fourth grade, fifth grade, you should have done this with your science teacher, or maybe you've just noticed it on your own. But I didn't use a pencil. I used a chopstick, but it's the same thing. When you put a chopstick or a pencil or something straight into a glass of water, you can see that the light rays make it appear to bend. The light rays make the pencil appear to bend just a little bit. I also have this clear rod here. It's a stirring rod that it's a little more, you can't even see it. I'm going to go, oh, well, there you can. All right, so you can tell that it's a little bit bent there according to the light. So why does that happen? Or, well, first, what did you see? It appears to bend. All right, so why does this happen? It happens due to refraction. Refraction occurs when rays of light move from one medium to another. So what two mediums? So we know that the light is going through the glass both times. But what are the two mediums that we're looking at when we look at the chopstick? What medium here? What medium here? Right. So it's water and air are the two mediums that it has to travel through. And because light travels at a different speed through water than it does through air, it appears to be bent. It slows down. So as the light changes medium, it changes speed. The change makes the light rays reflect to our eyes differently. It refracts them, it bends them, and it makes the object appear to bend. Again, get that if you need to. Pause it if you need to. I'm moving on. Some mediums cause light to bend more than others or refract. So we know that reflect is bounce, refract is bend. Reflect, bounce, refract, bend. Reflect, refract. Good job. Light travels fastest in gases and most slowly through solids. So the opposite of sound waves. We're going to model what is going on in our glass here by drawing some light rays down here. Okay, so through air, light moves at 12 million miles a minute. That's pretty darn fast. But then as soon as it hits the water, it slows down. And when it hits the glass, it slows down even more. But then what's crazy is, unlike sound waves, when it escapes out the other side, it can speed back up. So that's why we end up with that bend in the pencil, because once the light gets out of the water, it's like, oh, I'm free, and it stops bending. So this bending, or what's the word? Good job, refraction. So this bending or refraction of light rays as it changes mediums is what causes white light, which contains all colors of light, to be split, creating what we see as a rainbow. So when we see a rainbow in the sky, what's happening? Exactly. The light rays are bending through the water droplets that are in the air. So the sunlight is refracted through the water droplets. Another way to split white into all possible colors is using a prism. So I have included a link to this video in today's folder. I'm not going to play it now because it's going to make it all choppy, but I do want to show you. Do you see how that rainbow was up on the wall? Here, one more time. Show us the rainbow. Yeah, so they shine the light and then bam, there's the rainbow. Okay, but watch that video on your own. The link is in today's folder. All right, so going back to this, and now all right, so I used to keep a prism, and I don't know what's happened to it. But here's the thing: it never worked very well anyway because I don't have sunlight in here. I never was able to get a powerful enough flashlight to get a really good prism. So honestly, I'm kind of glad I found that video. At the same time, I know it's always better to see stuff for yourself in class, and so I wanted to show you something for yourself. So we're talking about light bending, right? And we've got this arrow here pointing this way, and we've got this thing of water. And I want you to notice what happens when the arrow passes behind, right? It's still pointing the same direction, is it? Isn't that crazy? So the light bends so much that it flips over the arrow and makes it appear to be facing the other direction. So I got to show you something, even if it wasn't a prism. All right, so if you haven't gotten that down, pause it, but I'm going to move ahead and we're going to model what happens in the prism. So we have our prism and the white light is going to go into the prism and then it gets bent through and it's going to turn into a rainbow. What are those colors? How do we remember it? What's the guy's name? Yeah, good job. Roy G. Biv is his name. And that's red, orange, yellow, green, blue, indigo, and violet. And then last but not least, I want you to draw a high frequency and high amplitude wave on this side and a low frequency and amplitude wave on this side. Pause and try it. All right, welcome back. This is what you should have drawn. Frequency means many waves. Amplitude means big waves. So a high frequency, high amplitude wave would be many big waves. So low frequency and low amplitude would be few low waves. All right, there is one more thing I want to show you before we close out for today. It's something that I had on the board over here for these folks, so I want to show it to you too. So we know that light can be absorbed, reflected, or transmitted. And we know that the types of objects are opaque, translucent, and transparent. Now, if I was to ask you, match those up. Draw lines to match them up. Typically, in a matching situation, it's a one-to-one match, but with this one, it's not, so be careful. We know that opaque objects absorb and reflect light. We know that light is transmitted by translucent and transparent objects. All right, so how do we keep that all together? Transfer, transmit, transportation. What's it all mean? To move. So what happens when light is transmitted? It is moved. It is moved through something. It doesn't bounce off. It It doesn't absorb, it is moved through. So translucent, transparent, transmitted. Those are the three that are all related because they all have the light moving through. And then opaque objects either absorb light or reflect light. And the light it reflects is the color that it shows. All right, that is it for Note 6A. Make sure you get those done and have them available for the quiz, which is going to be next week. The lab is going to be Thursday. So if you're going to be back in the building on Thursday, please make sure you have your hair up and wear closed-toed shoes. Have a lovely day. Make good decisions. Bye.